Okay, so this video is on Hilbert space because on my channel there are lots of quantum mechanics stuff, and very often I use the term Hilbert space without defining it on mathematical point of view. So it's mathematical lessons on Hilbert spaces. So we've seen previously in the previous lessons that what was normal vector spaces. We spoke about Banach spaces. We give some examples of that. We spoke about continuous function on an interval AB, and we've defined for p superior than 1 the LP space of n, which is all the sequences from k from 1 to infinity xk, such that the sum for k from 1 to infinity of the absolute value of xp at the power p is less than infinity. So this number is a convergent series. Okay. So we've seen also that a Banach space, which respect to the norm, which respect to this norm. So we define this is a norm. The norm of the sequences of xp, the p norm. This is the p norm. Okay. Is the sum for k from 1 to infinity of the module of xp at the power of p of the power 1 out of 1 divided by p. Okay. So example for x which belong to Rn, if we write x as the sequence, x1 as first coordinates, x2 as second coordinates, xn, so which is a series, but I speak about coordinates the same. We speak about Rn is a Banach space which respect to the norm, which is the norm of x, is defined as near 2. Okay, the sum for one for equal 1 to n of the absolute value of xk square at the power 1.5. So I recall you that Rn has an inner product, so it's a scalar product which is defined as follows. So if we make the inner product between x and y, x and y is a sequence of n number, okay, in Rn, okay. So we define the inner product so as the scalar product x and y, such as sum for k from 1 to n of xk yk. And we have also these properties that the inner product of x with itself is the square of the norm of x. So now we are going to see a generalization to arbitrary vector space. Okay, so let's take the definition, the following definition. So let V be a complex vector space. An inner product is a mapping. Okay, it's a mapping. This is the symbol of the mapping of the inner vector space that goes from V to V to C. Okay, so this inner product takes two elements of V and give us a scalar which is here a complex. Okay, so it's somewhere an application that takes two vector and give us a scalar, but this application has three properties. Okay, to be an inner product. Okay, so to be an inner product, we have the first properties, the second properties, and the third properties. So the first properties is the following. So whatever u, w, and in vector space, whatever alpha and beta in the complex corpus, okay, so scalar, we have the inner product of alpha v plus beta w with u is alpha, the inner product between v and u, plus beta, the inner product between w and u. Okay, so this is the first property, the first property to verify each time you want to verify that you have an inner product. Okay, now the second in an Hilbert space, of course. So now the second property is the following: the scalar product, the inner product between v and w, okay, is the complex conjugate of the inner product between w and v. Okay, this is very important, especially when in quantum mechanics. It's a property that you use many times when you speak about Hilbert space. Yes, okay. So by the mathematical point of view, you also need to verify this property to check if you have you have a right inner product. Okay. So now the third property. The third property is the following. Okay, the inner product is an inner product if the inner product of V with itself is always a positive number. Okay, it's always a positive number. So whatever V you take as a vector in the vector space, and whatever you have the inner product between V and V equal to 0, then and it's a binary condition, then V equals to 0. On the other way, if V equals to 0, necessarily the inner product of V with itself is equal to 0. Okay, so there are three properties, and you can't do one without the other. So these three properties are linked, and these are the three properties you need to verify in order to verify that you have an inner product. Okay. Well, so let's take some example now. First example, let's take Rn, which is a vector space with an inner product, okay? And Cn, which is a vector space with an inner product too. So this is the inner product that is defined for Rn and Cn. So the inner product between x and y, when in Rn or Xn, okay, you have x by the coordinates x1, x2 up to xn, and y as is a vector which has n coordinate, which are y1, y2, y3, etc., up to y1, yn. Okay, so this is the sum from k from 1 to n of xk multiplied by the complex conjugate of yk. Okay, so it's very important because you are speaking about an inner product in an Hilbert space. Okay, so this is the definition of the inner product in Cn. Okay, of course in Rn you don't need to take the complex conjugate because every complex conjugate of in R is itself. Okay, that's not the case, the same in Cn. So we define generally this inner product for both of them. So let's prove now for Cn that this inner product I just defined with you correspond to an inner product, which means that verify the three hypotheses, okay, of the inner product. So let's verify first one. So let's take, okay, of course we see it's obvious that with this definition the inner product between as it is defined between x and y is an element of the complex number. Okay, why? Because its product, its k by yk complex conjugate is an element of a complex of the complex curve. So a fortiori, the sum of all these elements are elements of C. Okay, so it's obvious, but we have to say it, in a copy. Then first verification. So alpha and beta are scalar, x, y, and z are vector. Okay, so let's take the inner product as defined like this between alpha x plus beta y and z. So so I just write this with the right elements is the sum from k from 1 to n of alpha xk plus beta xk multiplied by the complex conjugate of zk. Okay, now this sum can be split into two sums. Okay, we can split this sum because of the distribution of the multiplication in the C curve. So I can write this sum as alpha. So I isolate alpha, I put alpha out of the first sum because alpha does not depend on the index of k. Okay, alpha is not dependent of k. So it's equal to alpha, the sum for k from 1 to n of xk, the complex conjugate of zk. Okay, plus it's the same for the second part of this summation. I use the linearity of the summation, and I use also the distributivity of in the C corps, that you know these rules, okay? That's basic rules in R and C. Okay, so plus beta sum for k from 1 to n of yk, the complex conjugate of zk. But this you can see, okay, that it's this sum is nothing more than the inner product as I define it between x and z. Okay, here you can see it, and this sum also is no more than the inner product between y and z. Okay, so we just verified the first definition of the inner product, which means that the inner product between alpha x plus beta y and zeta, where alpha and beta are scalar, are in the C corp or R corps, and x, y, and z are vector, that this sum can be split in alpha inner product between x and z plus beta inner product between y and z. Okay, so we are our first definition. So now let's verify the second one, which is that the inner product between v and y is the complex conjugate of the inner product between y and v. Okay, so let's verify, let's check it. Okay, in a copy, if you are asked to verify that you have an inner product in an Hilbert space, you have to verify these properties. Okay, it's the way the examiner will see if you understand and give you the maximum points for your copy. So the inner product between x and y is the sum for k from 1 to n, by my definition, the product between xk and the complex conjugate of yk. Okay, but I can also write this sum as the complex conjugate of what? Of the sum for k from 1 to n of xy, yk complex conjugate, okay? Because you always know that the complex conjugate of A is A itself. Okay, if you apply 2 times the complex conjugate, and also the complex conjugate of the product of two numbers is the product of the complex number conjugate of the numbers. Okay, and this is nothing more than the complex conjugate of what? What is that sum? That sum is nothing more than the inner product between x between y and the complex conjugate of y. Okay, so we just define that the inner product between x and y is the complex conjugate of the inner product between y and x. Okay, so now let's verify the third definition. Okay, that match an inner product. So which means that the inner product between v and itself is always positive. Okay, and whatever v, the inner product of v with itself is equal to 0, means that v is the null vector. Okay, remember that the inner product is a scalar. Okay, but you take two vectors to make an inner product, and you have a scalar as a result. Okay, so let's take the inner product of x with itself. Okay, the inner product with x between x and itself is nothing less than the sum of the absolute value of xk square, and of course whatever number you take, the absolute value of square of a number square is always positive. So the sum of positive number are always positive number. So you just verify the first thing. So now for the second one. So let's suppose that the inner product between x and itself is equal to 0. Okay, but this is equivalent to say that whatever k coordinate of x is equal to 0. Okay, because you can't have a coordinate that is not equal to 0, which means obviously that your vector is not the vector null, the null vector. Okay, so this is equivalent to the fact that x is equal to 0, and that's all. Just observe now this fact, because you need to manipulate it, especially if you make some kinds of quantum mechanics stuff. Okay, it's very useful, and you use it very often in quantum mechanics. Okay, but these are mathematical properties in the inner products defined in an Hilbert space. Okay, so let's observe that the inner product between V and alpha W plus beta U is equal to the complex conjugate of the inner product between alpha V plus beta U and V. Okay, so I use inside the inner product the linearity, okay, as it is defined before. So under the complex conjugate, I have alpha inner product between W and V plus beta inner product between U and V. Okay, always keep in mind what are the objects you manipulate. You manipulate alpha and beta, which are the same kind of objects, which are scalar. Okay, the scalar, real, complex, one component, one number. And between these parentheses, you have the inner product between two vector. Okay, vector. Okay, it's different. So for the same reason as I mentioned before, the complex conjugate of a sum of a complex is the sum of the complex conjugate. Okay, so I can split this sum into sum, and so this is the complex conjugate of alpha multiplied by the complex conjugate of WV, but the complex conjugate of WV is the inner product between V and W, okay, plus the complex conjugate of beta multiplied by the complex conjugate of the inner product between U and V, but the complex conjugate of the inner product between U and V is the inner product between V and U, okay? So let's just observe that and use it in your calculus, okay? So now I recall you what is defined in R2, the scalar product. So I just describe two vector, you know, in a two space. In R2 we can define two coordinates, you know, x and y in Cartesian, and I suppose that that the angle between x and y is theta. Okay, so I remember you that you calculate the inner product in R2 like this. So the inner product between x and y in R2 is the product of the norm of x and the norm of y multiplied by the cosinus of theta. Okay, so in this figure. So I remember you also that you have this inequality, which is very, very, very important for calculus. You know, in many examples, when you manipulate inner products, you use it very often. You know, not only in quantum mechanics, of course. So the absolute value of the inner product between x and y is always less than the product of the norm of the respective vectors. Okay, so it's inferior to the norm of x of the norm of y. But remember that you can have the norm of a vector by making the square root of the inner product between this vector and itself. Okay, so this is very important to keep in mind. To keep in mind this, that the norm of y is also the square root of the inner product between y and itself. Okay, so we can have some kind of now similar result in vector space. So let's speak about this very, very important theorem, which is the Cauchy-Schwarz theorem. Okay, and so generalizing this, which is only in R2 in Rn, okay, or in Cn, in the complex Cn, we can say that this is the theorem of Cauchy-Schwarz, that the absolute value of the inner product between the vector u and w is always less than, of course, this is a number, okay? When you make this inequality, this is a number. Don't forget that the inner product is a number. It keeps two vectors from the vector space and it gives you a number. This is a number. This can be a complex number, and you speak about the module, but if it's not a complex number, this between the cross is not a module, is the absolute value. Okay, so I speak here about the absolute value because I speak in Rn, but generalizing the absolute value, it's the module. Okay, so we can say that the module between the module of the inner product between u and v is always less than the square root of the module or the square root of the inner product between u and itself and u multiplied by the square root of the inner product between w and itself. Okay, so now we've got a lemma. If the vector space V has the inner product defined, okay, like this, then we have always that the norm of a vector V is equal to the square root of the inner product of V with itself. It is a norm, and let's prove it. Okay, let's prove it. So this is the what make a norm in reality. So you have to verify 3 axioms. Okay, so if we keep this a norm is an application that take a vector and give a real number. Okay, this is a norm. So first rule, the norm of a vector is always positive. Okay, and then if the norm of a vector is positive, then this vector is null. If this vector is the vector null, the null vector, then the norm of this vector is equal to 0. The 0 of R, and this is the 0 of the vector space, okay, which are 2 different objects. Don't confound them. Don't be confused, okay, with that. The 0 is the 0 in the vector space. The 0 is the 0 in the real, as you know, the natural element. Then, if it's a norm, you have, if you take alpha, a scalar which is either real or a complex, okay? So norm of alpha v is equal to the module of alpha, if alpha is complex, or the absolute value of alpha if alpha is real, multiplied by the norm of v. Okay, so this is the second axiom you have to verify, to check in order to determine whether you are in presence of a norm or not. Okay, and finally the third one is the so-called, Cauchy-Schwarz inequality at the end, which is known, in French, I give you as the inequality triangular inequality. Okay, I can say. So the norm of V plus W is always less than the sum of the norm of V plus W. Okay. So first one, and don't forget that we just defined that. So first one, of course, we see that it's obvious that the square root of the inner product between U and its and U belong to R. Okay. Then the norm of the vector is positive always, and saying that the norm of the vector is equal to 0 is equivalent to say that the vector is the null vector. Okay, by definition of 1. Now the second axiom. Okay, so the norm of alpha v, okay, is the square root of the inner product between alpha v and alpha v. Okay, alpha is a complex number, v is the vector. Okay, when you multiply alpha by a vector, you multiply indeed, in fact, each component of this vector by alpha. Okay, so but this is nothing less than alpha multiplied by the complex conjugate of alpha. Okay, because you get at alpha because of on F and cisquilinear, the alpha gets out of the product of scalar product and become alpha complex conjugate, multiplied by the square root of V of the inner product of V by itself. Okay, so which definitely is equal to, at the end, the module of alpha square by the norm of the vector V square at the power 1.5. So which is the product of the module of alpha by the norm of V. Okay, which is what we wanted to demonstrate. So now for the third inequality. Okay, let's demonstrate it. So we've got that the square of V, of the norm of V and W, is nothing less than the inner product of V plus W applied to itself, to V plus W. Okay, so now I use the linearity of the inner product. So this can be decomposed, okay, as two sum. It can be, so this is the the sum of the inner product between V and W, and the inner product between W and V and W, okay? But this is also, so I decompose it a second time, I distribute in a way. So this is the module, okay, or the absolute value, the module of a sum of force inner product, V and V for the first inner product, V and W for the second inner product, and W and with V with the third inner product, and W with the last inner product. You know and you understand very well that the order is very important. The inner product of V and W is not the inner product of W and V. It's not symmetric, okay? There is the complex conjugate, okay? But this can be uh, measured by, okay, this is inferior to the sum of the absolute value, because you know that the absolute value of A plus B is less than the absolute value of A plus the absolute value of B, of course. So it's less than the sum of this absolute value, okay? And what is the absolute value of the inner product between V and V? It's nothing less than the norm of V of V square, okay? And then for this one, it's the norm of W square, and this 2 1 can be R equals to, R equals can be measured by 2 times the product of the norms of the vector V and W, okay? Which at the end, this is a remarkable identity, which you all know, of course. So this is nothing less than the square of the sum of the norm of V and the norm of W, okay? So at the end, we we demonstrate, because we have the square, okay? We take the square, so A square is less than B square, so at the end A is less than B, okay? For AB positive, of course. So at the end, we demonstrate that the norm of V plus W is less, inferior, or equal to the sum of the norm of V and W, okay? Now, by using 3 and 4, we can recover the inner product from the norm. And this is very important to understand that the inner product can be recovered by the norm. So I give you some more inequalities, Cauchy-Schwarz inequality, that are quite often used in exercise or also in quantum mechanics, but so it's good to know them, and it's also good to know how to demonstrate them. So I give you them. So there is what is known as the parallelogram law. Okay, what is the parallelogram law? Is this one? So the square of the norm of V and W plus the square of the norm of V less W is equal to 2. It is equal to 2 times the sum of the square of V and the square of W. Then there is the polarization identity. Okay, and this is the polarization identity, okay? Well, you just expand the inner product between V and W, so you have 1/4 of this sum, just expand it, and at the end you've got that the inner product between V and W is nothing less than 1/4 of 1 divided 4, so 1/4 of the difference between the square of the inner product between the square of the norm of V plus W less less the square of the norm between V and W, okay? Not all norm vector space have an inner product, okay? This is important to keep it in mind. And if the parallelogram rule is not satisfied, then we are dealing with do not come from an inner product. But this is less important, okay? So let's now talk about a lemma. If a vector space has the inner product defined, then the norm of vector V of this vector space is equal to the square root of the inner product between V and itself, and this is a norm. So now definition. A Hilbert space. What is an Hilbert space? A Hilbert space is a vector space with an inner product which has a Banach space with respect to the norm with the associated norm which is the norm of V defined as the square root of the inner product between V and V. So this is the definition of an Hilbert space. Okay, so let's see some example of Hilbert space. Rn is an Hilbert space, Cn is an Hilbert space. Okay, and the inner product, so between x and y, is defined as follow, as you see, as you have seen previously. And so it's the sum for k from 1 to n of xk yk complex conjugate. So now consider infinite sequences. So I consider x as the sequences x1, x2, xn, which is the sequences of all the xk for k from 1 to infinity. So we've speak about, of course, about norm vector space. Okay, Banach space. We give some example of a continuous function between on a segment AB. We define for p superior to 1 the LP space, LP of n, which is all the sequences that are converging with the p norm, okay, which means that sum for k equal 1 to infinity of the xk at the power p is less to infinity. We define then a Banach space with respect to the norm. The norm of the sequences of xp, the p norm, is the sum for k from 1 to infinity of the xp or xk at power p at the power 1 over p. L to the n is an Hilbert space with respect to the norm. So with respect to the norm, which is the inner product between the sequences of xk for k from 1 to infinity and the sequences of yk k from 1 to infinity. And this inner product can be written as you see, and is, when you make the calculus, is the sum from k to 1 to infinity of the product of the coordinate xk of the component xk of x multiplied by the complex conjugate of the component yk of y. Okay, so proof of that. So we first must show that the inner product is well defined. That is, we must prove that the sum of xk complex conjugate of yk is convergent. So we have the inequality, the sum for k from 1 to infinity of the module of xk complex conjugate of yk is inferior to the product of two infinite sum. The first one is the sum for k from 1 to infinity of the module of xk square at the power 1.5, and the second one is the sum for k from 1 to infinity of the module of xk square power 1.5 is less than infinity. So these are known as the Holder inequality, okay, for p and q equal, for p plus q equal 2. Now let's generalize this inequality. I give you the generalization, okay, but I don't demonstrate it. Okay, so the Holder's inequality is the following: whatever p and q belonging to 1 to infinity with 1 over p plus 1 over q is equal to 1, we have that the sum for k over 1 to infinity of the absolute value of xk yk is less than the sum for k for 1 to infinity of the absolute value of xk at the power of p at the power 1 over p multiplied by the sum for k over 1 to infinity of the module of yk power p at the power 1 out of q, power q, sorry, it's p and q here, okay? So there is also another inequality generalized, which is the Minkowski's inequality, okay? And this is the Minkowski's inequality. For whatever p belonging to 1 to infinity, we have that the sum of the module of xk and yk at the power of p, at the power 1 out of p, okay, this is the sum, okay, these are the parentheses, okay, this is very important, is less than the sum of two infinite sum. The first infinite sum is the infinite sum between, so over k of the module of xk at the power p, and all of that is at the power 1 out of p, plus the sum for k from 1 to infinity of the module of x of yk at the power q, all at the power 1 out of q. Okay, so the sum xk yk complex conjugate is absolutely convergent and therefore is convergent. Okay, the rest of the proof is exactly the same as for Cn, so you can do it. So the first lecture we speak about operators, normal space, normal vector space. We speak about Hilbert space. The notation commonly used for Hilbert space is this one. Okay, calligraphic notation, which is common to French, English, Italian, Spanish, I mean all the community of mathematicians. We usually use it like this. Okay, so let's consider now a linear operator, which is the phi linear operator between an Hilbert space and a complex of a complex, which take a inner product. Okay, and gives us in a norm vector space, which is C here. So this is an Hilbert space which have an inner product, and with respect to the norm, as the norm of V is the square root of the inner product between U and itself. Okay, the norm is the absolute value. Okay, so definition. What is a bounded linear operator? Okay, let V1 and V2 be norm spaces. A linear operator T is an operator that take V1, that take a vector in V1 and give a vector in V2. Okay, and this linear operator is bounded if there exists a constant k, such as the norm in V2 of T applied to V is a vector of V2 of V1. Okay, T of V a vector of V1, but we took the norm of T of V, but T of V is an object that belong to V2 now. Okay, that belong to the space V2, so that's why it's the V2 norm. It's less that k is obviously a real positive number multiplied by the norm of V the V1 norm, because V belong to V1. Okay, so it's very important, the indices. It's very important to understand that T is an operator, that T is linear, and as an operator, take a vector in the vector space V1 and give another vector, because T of a vector in V1 give a vector in V2. Okay, so this is important to know it, to understand the object, the mathematical object that you are dealing with. So the smallest possible value of k is called the norm of the operator, and is denoted the norm of T. Okay, so the norm of an operator is the minimum value of k. Okay, this is the norm of the operator. We say that phi is bounded if there is a constant k positive, such that, okay, so this is a notation. So the norm in C of phi applied to V is less than k. Okay, k is a constant positive, multiply by the norm of V belonging to the Hilbert space H. Okay, it's more or less the same as what we write in here. Okay, so now let's take some example to make it clear, to have a clear mind about the object we are dealing about, the mathematical object we are speaking. So let W belonging to an Hilbert space. Okay, so W is a vector that belongs to an Hilbert space H. And now let's define the operator phi acting on V. Now phi is an operator acting on a vector from the vector space. Okay, that give us, okay, a scalar, a complex number, which is nothing less that the inner product between V and W. So phi is in a way linked to W, okay, because with whatever V you take, you got the inner product between this, the V you take, and W. Okay, so then phi is linear and bounded. Okay, So I say as an exercise, you can try to demonstrate that phi is linear and bounded. It's quite easy. You just have to do what I've just done in the previous section. Okay, so phi is linear. You take alpha, you take beta, you take v, w. You check that phi of alpha v plus beta w is equal to alpha phi of v plus beta w. It's very simple to check it with the linearity, with the properties of the scalar of the inner product. Okay, and bounded too. Okay, another example, which is an important example. Let's take the sequences of vk. Okay, vk from k from 1 to infinity be a sequence of unique vector in the space, in the Hilbert space. Okay, so the norm of vk is 1, is equal to 1, whatever the k you take. So let's put that phi, the operator phi, okay, is acting on an Hilbert space. So it takes a vector from an Hilbert space and give us a complex, which is the sum from k from 1 to infinity of 1 over k square multiplied by the inner product between v, okay, the vector v, and vk. Vk is the component, the k component, okay, of v. Okay, then first, phi is well defined. We are going to verify this, of course. Then phi is linear. Then phi is bounded. Okay, let's demonstrate the first axiom, the first assertion. Phi is well defined. Okay, you must show that sum of 1 over k2, k is belonging, k of course different to 0, huh? Multiplied by the inner product between v and vk is convergent. Okay, and you have whatever k, the inner product between vk and vk is equal to 1, because the norm of vk is equal to 1. Okay, so we have to see that this series is convergent. Okay, this series is convergent if we are going to see the absolute convergence. Okay, so sum for k from 1 to infinity of 1 over k squared multiplied by the inner product between v and k is always less than sum for k from 1 to infinity of 1 divided by the square of k multiplied by the norm of v multiplied by the norm of vk of vq vk. Okay, but this is nothing less, because the norm of vk is 1, of the sum from k from 1 to infinity of 1 over k squared multiplied by the norm of v. I remind you the Cauchy-Schwarz inequality that we are using here. The square of the norm of v and w is equal to the inner product between v plus w and itself. Okay, and this inner product can be decomposed and of the inner product between v and w plus the inner product between w and w plus the inner product between v and w plus the inner product between w and v, which is inferior or equal to the square of the norm of v plus the square of the norm of w plus the absolute value of v and w plus the absolute value of w and v, which is inferior or equal to the square of the norm of v plus the square of the norm of w plus 2 times the norm of v by the norm of w, and this is nothing less than the square of the norm of v plus the norm of w. Okay, so we have, and this is, you have to know it by heart. Okay, this inequality, you have not to know how to demonstrate it, but you have to keep in mind always you can use it, okay, without justify it, obviously in the calculus when you do quantum mechanics, for example, but not only. So whatever v and n and belonging to the natural the integer, so the inner product between v and w is always less, if equal to the product of the norm of v and norm of w, and the sum for k from 1 to infinity of 1 over k square multiplied by the norm of v is less than infinity, because the sum of 1 over k square is convergent. So sum for k from 1 to infinity of 1 over k square multiplied by the inner product between v and vk is absolutely convergent, and therefore is convergent. So now let's demonstrate the second assertion. So we have to keep in mind what you want to demonstrate. We start from phi of alpha v plus beta w, where alpha and beta are scalar complex and v and w the complex, and we want to demonstrate that this is equal to alpha phi of v plus beta phi of w. So if you keep in mind in a clear way what you want to demonstrate, you just do the things. You just write the things. Okay, it's easy. Well done. So this is the sum from k from 1 to infinity of 1 over k square multiplied by the inner product between alpha v plus beta w and vk. But we use here the linearity. This is I forgot here, I suppose. Let's see. I don't know, because it's on the left. If the alpha and beta were on the right, we would have the complex conjugate here. Okay, don't forget that because alpha and beta are on the left in the inner product. When they get out of the inner product, they get out without the complex conjugate. But because we are in an Hilbert space, if you make the scalar product, the inner product, and on the right, you would have if it would have been for example v scalar product alpha v plus beta w, it would have become the complex conjugate. Okay, that's why we don't have the complex conjugate here. Okay, so this can be split into sum. Okay, it's the sum from k from 1 to infinity of 1 over over k square of alpha, the inner product between v and vk, plus beta by the inner product between w and vk. Okay, so this is equal to alpha is not depending of the indice, so I can get it out. I use the linearity of the summation. Okay, so it's equal to alpha sum for k from 1 to infinity of 1 over k square, the inner product between v and vk, plus beta sum for k from 1 to infinity 1 over k square, the inner product between w and vk, which is equal to alpha phi v plus beta phi of w. Okay, so now let's demonstrate the last action. So the absolute value of phi of v, okay, phi applied to v, and don't forget that phi is a linear operator, okay, that apply to a certain vector v belonging to a certain vector space, which is an Hilbert space. Okay, an Hilbert space where we define an inner product and a norm. Okay, so this is the absolute value of the sum of 1 over k square multiplied by the inner product of between v and vk. Okay, so this quantity can be is inferior to, because of course the absolute value of a plus b is less than the absolute value of a plus the absolute value of b, is inferior to the sum for k from 1 to infinity of the absolute value of 1 over k square multiplied by the inner product between v and vk. Okay, so this is less of the sum for k from 1 to infinity of 1 over k square. So we use the inequality, the Cauchy inequality, so this inner product can be less than the product of the norm of the vector. At the end, we know that the norm of vk is equal to 1 by constriction, by definition, by assumption in the exercise. So this is inferior to the sum from k from 1 to infinity of 1 over k norm of k. The norm of v. The norm of v can be get out of the sum, and so phi is bounded. Why? Because this sum is independent of v, and you know that the sum for k from 1 to infinity of 1 over k square is nothing less than the square of p divided by 6. Okay, so you say that phi of p is less than k from multiplied by the norm of V, so phi is bounded. So all bounded functional have the form in the example that we just mentioned. So now let's speak about the theorem. Let phi be any bounded functional. Then there exists a unique vector W, okay, belonging to our Hilbert space, such as W, such as phi of V is equal to the inner product between V and W. In example, we have taken W, which is equal to the sum for k from 1 to infinity of 1 over k square Vk. Okay, so this is all for this lessons about Hilbert space. I clearly make these mathematical lessons because I use lots of quantum mechanics in my channel, as you can see, and it was very important to define precisely with some example what were Hilbert space. I think I will follow these mathematical lessons by speaking about the adjoint operators and the all adjoint operator, because in quantum mechanics we use them too. That's all for these lessons.